Welcome to The Explainer. Today, we are diving into the invisible rules that, well, run pretty much everything. I mean, think about the arc of a football or even the orbit of a planet. It all boils down to two key ideas: force and motion. So, what is it that makes a dragster rocket off the line? Or what happens when a quarterback gets tackled? Or even when a car slams on its brakes? These things seem completely different, right? But believe it or not, they're all connected by one single powerful idea. At the core of every single one of these actions is just a simple push or a pull. And in physics, we have a name for that. It's called a force. So here's our game plan for today. We're going to start with the basics. What is a force? Then we'll walk through Newton's three big laws, one by one. And to wrap it all up, we'll see how this all connects to the stuff we see every single day. All right, first things first. What exactly is a force? Well, to put it simply, it's the hero of our story. It's the reason anything ever changes its motion. It's what makes stuff speed up, slow down, or change direction. I mean, seriously, without forces, the universe would be, well, pretty boring. Nothing would ever change. Okay, so here's the more official definition. A force is just a push or a pull that one object puts on another. Think about it. It's the force from the track that pushes on a dragster's tires and makes it just explode forward. Or on the flip side, it's the force from a telephone pole that acts on a car to bring it to a very sudden, very dramatic stop. But, in the real world, things are rarely that simple. Most of the time, an object has a whole bunch of forces acting on it all at once. So to figure out how it's actually going to move, we have to add up all those individual pushes and pulls to get the combined effect. And this total overall force, that's what we call the net force. Okay, so that leads us perfectly into Newton's first law. Now, for a really long time, people thought that the natural state for any object was just to be stopped, at rest. And it kind of makes sense, right? If you push something across the floor, it slows down and stops. But Isaac Newton came along and realized, wait a minute, we're all missing something here. See, that old idea felt right because of this one sneaky force: friction. You slide a book, it stops. To keep it going, you have to keep pushing. But Newton had this amazing thought experiment. He imagined a world with no friction. Think about a hockey puck on a perfectly smooth sheet of ice. If you give it a push, it would just glide forever. And that's the big aha moment. Objects don't naturally want to stop. It's friction that's forcing them to. And this all leads us to the official statement of Newton's first law. It says that if the net force on an object is zero, then its velocity can't change, it can't accelerate. So what does that really mean? It means an object at rest is going to stay at rest, and an object that's already moving is going to keep moving in a straight line at the same speed forever, unless, of course, some outside force comes along and messes with it. And that tendency to just keep doing what it's doing, that's what we call inertia. So law number one tells us what happens when there's no net force. But what happens when there is a net force? Well, that's where Newton's second law comes in. And this is the one that really gives us the power to calculate and predict how things are going to move. But before we get to the law itself, we need to be super clear on one thing: mass. Now, mass is not weight, it's not size. Mass is really a measure of an object's inertia, how much it resists being accelerated. You totally get this intuitively. Imagine trying to kick a baseball. Now, imagine kicking a bowling ball with that exact same force. Ouch. The baseball is going to fly, right? It's going to accelerate way more because it has less mass, which means it has less resistance to changing its motion. And that brings us to the big one, probably one of the most famous equations in all of science. F net equals m times a. It looks so simple, doesn't it? But it is incredibly powerful. It's the mathematical link between those three key players we've been talking about: the net force on an object, the object's mass, and the acceleration it's going to experience as a result. This little equation, it's basically the engine that drives all of classical mechanics. So how do we actually use F equals ma? Well, physicists have this awesome tool called a free body diagram. And the idea is just beautiful in its simplicity. You take the object you're interested in and you just represent it as a single dot. Then you draw arrows or vectors for all the outside forces that are acting on that dot. It's a way to cut through all the noise and focus only on what you need for Newton's second law. And this whole process really breaks down into a super reliable four-step method. Step 1, isolate your object. Just pick the one thing you're analyzing. Step 2, draw your free body diagram with all the forces. Step 3, add up all those force vectors to find the net force. And finally, step 4, plug it all into F net equals ma and solve for the acceleration. Seriously, this is the recipe for solving tons and tons of physics problems. All right, so we've covered what happens when there's zero net force and what happens when there is a net force. Now it's time for the third law. And this one reveals a really fundamental truth about the universe. Forces never, ever show up alone. They always come in pairs. I bet you've heard this one before. For every action, there is an equal and opposite reaction. Well, this is it. This is Newton's third law. When you push on a wall, guess what? The wall pushes back on you with the exact same amount of force. When a rocket shoots hot gas downwards, that gas pushes the rocket upwards with an equal and opposite force. It's everywhere. Now here is the most important part, and honestly, it's where most people get tripped up. These action-reaction pairs, they always act on two different objects. The action is on one thing, and the reaction is on the other. So my push on the wall is on the wall. The wall's push on me is on me. Since they're not acting on the same body, they can't cancel each other out. And that simple, crucial rule is behind literally every interaction in the universe. Okay, so now we've got the 3 laws of motion under our belt. Let's put it all together and see how this stuff applies to the forces we actually deal with in our daily lives. And let's start with the big one, the one we feel all the time, gravity. The gravitational force, or Fg, is simply the pull that the Earth exerts on any object. It's always directed straight down, right toward the center of the planet. And this force is what we experience as an object's weight. And this leads to an absolutely critical distinction that we need to be clear on. Mass and weight are not the same thing. Your mass is the amount of stuff you're made of. It's measured in kilograms, and it's the same no matter where you are in the universe. Your weight, on the other hand, is the force of gravity pulling on that stuff. It's measured in newtons. So if you go to the moon, your mass stays the same. But because the moon's gravity is weaker, you weigh a whole lot less. So wait a second. If gravity is constantly pulling you down, why aren't you falling through the floor right now? Well, the answer is another force called the normal force. When you stand on a floor or sit in a chair, that surface pushes back up on you. That push is the normal force. And it's called normal because in math, normal means perpendicular. This force always pushes perpendicular to the surface it's coming from. So just think about it for a second. Right now, as you're sitting there watching this, you are a perfect, living example of Newton's laws. Earth's gravity is pulling you down, but your chair is pushing back up with a normal force that is equal in magnitude and opposite in direction. The net force on you is 0, so your acceleration is 0, and you stay put. That's Newton's first law, playing out right now. It makes you wonder, right? What other invisible forces are shaping your world in this very moment?